All right, thank you very much. Next up, we have Chris Tracy from ESNet talking about 100 gig.
Hello there. Now for something completely different, I think. Where's the clicker? Right.
It's right there, yeah. Just the big green button on top.
Okay, thank you. Hello, good afternoon. I'm Chris Tracy from ESNet, AS293. Going to be talking about 100 gig today and our experiences. So just to I have to apologize. The title of this talk might have been somewhat misnamed. It might have led you to believe that we are just experimenting with 100 gig, and that's actually definitely not the case. We're actually right in the middle of deploying a production 100 gig backbone across the nation. So much of this material and our operational experience was built on our initial experiences with deploying this coast-to-coast prototype 100 gig network. But just in a few months, this will all be transitioned to production quality 100 gig network. So I'm going to talk about a few things that we learned with our initial turn-up, but I just wanted to clear up any confusion about whether or not this is a real network, because it is. This is just a quick outline of the talk. I'm sure you're all capable of reading, so I'm just going to get on with it and start into a quick overview of what we call ANI and ESNet 5. So ANI, or the Advanced Network Initiative, was a ARRA-funded program that was intended really to accelerate the commercialization of 100 gig by deploying a nationwide 100 gig backbone. And so what we essentially have today is a pre-production 100 gig network that has 100 gig circuits stretching across the country. It links the three major Department of Energy supercomputing centers shown here in the red circles. Those are NERSC, Argonne, and Oak Ridge. And we also have a 100 gig connection to the International Exchange Point known as Manland in New York. So separate from we basically have another entirely dark footprint which spans the nation. This is actually a separate fiber pair that's mostly congruent to the lit network that I'll talk about in a few moments. With the exception of some metro strands, this fiber is completely dark. We're actually actively looking for researchers and/or vendors to work with us, to submit proposals, to use this to do field trials and prove out technologies like flexible grid ROADMs and terabit lambdas, things like that. Finally, we have an experimental testbed that's deployed at three locations, at NERSC, Argonne, and Brookhaven. This basically consists of high-performance hosts that are capable of sourcing and syncing traffic at up to 100 gig per second. We have a bunch of OpenFlow switches, virtual machine hosts, for OpenFlow controllers, conventional routers and switches, all sorts of things that you might want for doing different types of research on networks, even some layer 1 optical gear. The primary purpose of this testbed is really to facilitate network research, and like with the dark fiber footprint, we're actually actively supporting a number of different funded research projects who are actually using this infrastructure to support their work. And finally, it's also very helpful for our own engineering staff because we also get access to all these resources for our own testing and development. I'm not sure how many people here are really familiar with the Supercomputing Conference. For those that aren't, just stay with me. There's basically a big conference every year in November, very much focused on high-performance networking, high-performance computing. All the big networking vendors are there. All the big high-performance computing vendors are there. It's a big conference, 10 to 15,000 people probably. And every year, there's always a big push to see, how fast we can make the network that year. And so at the last supercomputing in 2011, it was in Seattle. What we essentially ended up with at the end were 700 gig circuits, one of which went all the way into Seattle. I'll talk a little bit more about the engineering of that link at the end. And so we basically turned up 700 gig waves that are depicted here in the map. The smaller green dots are showing the locations of the optical add drop points. In this particular case, the small dots ended up being the 100 gig regens in the middle of the longer circuits, really. The circuits terminate on the larger dots, which are shown here. So the larger dots are also optical add-drop points, but they really show where we deployed 100 gig routers at for this, to build this network for supercomputing. This is basically where the client handoff from the optical transport gear to the router occurred. So moving on, this is that was sort of a quick overview of ANI, and now where we're going with this is really to what we call ESNet 5. Throughout that whole rollout of the prototype network I just discussed, our intention has always been to basically build something that would ultimately be transitioned to production and form the core of our next generation network. So ESNet 5 is ultimately what ANI will morph into, and this will completely supplant the current network known as ESNet 4. So this map is showing the optical design. This essentially consists of 13,000 miles of lit fiber, all of which is lit by equipment that we can control and manage. The wave capacity across the network, across the black lines, is actually shared with our partner Internet 2. So what we've done is on these links we've divided the wave capacity, and so the system is engineered for full fill. So we divide it up to between 88 channels. We get 44 each at 50 gigahertz spacing. On some portions of the metro rings, we have it's actually solely owned by ESNet, so we have a full channel capacity to ourselves there. So as of today, last I checked, we were over 200 amp nodes deployed across this network. There's still some work that remains along the West Coast. I think it's Seattle down to LA or so. A lot of nodes are, I think, still in the process of being brought up. I think we're anticipating about over 300 or maybe 350 amp nodes at when everything is finally finished being built. Out of all those nodes, we also have a bunch of add-drop points shown by the black circles, and these are essentially where we can add-drop client signals and install transponders, and so these are essentially MEMS-based multi-degree ROADMs that utilize wavelength selectable switches. And what they can do is, they can either all optically pass channels from one degree to the other. They can locally add drop channels and either connect to clients or form regions for long circuits. And 15 of these nodes, particularly in the metro areas, have what we call directionless capabilities. By directionless, we really mean that waves that terminate on that node can actually be optically rerouted either east or west without physically moving any fiber at that site. So this is particularly useful in the metro areas where we might want to actually reroute circuits in the event of fiber cuts, since we're provisioning all these circuits without any kind of protection. So we're getting close to working our way here up to layer 3 here. In a couple of slides, you'll actually see how all of these 2,300 gig circuits, see where they're all actually landing at and where all the routers are deployed. But shown here are just 2 examples of 100 gig circuits across the wide area as well as the metro. These circuits are handed off to 100 gig routers. They're deployed at the endpoints of these circuits. And if the circuit extends quite far, like that one from Sacramento to I think it's Denver, there's usually one or more regions required along, somewhere in the middle to ensure an error-free link. And so currently we're targeting 23 lambdas to turn up by the early fall of this year. So in total, to support all those 23 circuits, we obviously need to have transponders where they terminate, but for many of these, we also required a lot of regions in the middle. And so at 100 gig, the cost for this can really add up quite quickly. As much as possible, we've strived to minimize the number of overall regions by using optical modelers and carefully selecting the hardware. In some cases, even having to wait possibly till a better version of an amp or something might come out that gives us better performance, for example. So here's a picture of the routed network. Basically, what we're just moving along up the stack here. Our current target right now is 20 routers that are going to have 100 gig interfaces. The orange circles with the number 100 in them actually show the location of all those routers. And across those 20 routers, we're deploying 52 layer 3 100 gigabit Ethernet interfaces. So all those solid blue, the thick solid blue lines show they represent basically a single 100 gig lambda across that DWDM optical transport layer, connecting 200 gig routers. And similarly, the thick purple lines are the same in the metro areas. So you may or may not be surprised, we actually have 3 customer sites that are shown here that actually own their own 100 gig router that actually connect to us at 100 gig. And yes, they have actually shown they are capable of even filling this up with real applications that are not just iPerf. And finally, we have, let's see, I think we have 200 gig exchange point interconnections, one at Starlight, one at Manlan. We're expecting it to take some time to really see any significant traffic on these, but we've already brought these up. The red stars show places where we're anticipating more of these 100 gig peering points to other RNE networks. Okay, so that's just sort of an overview of ANI and ESNet. Now I'm just getting more into the meat of the topic here. So just taking a step back from a high level, the transport system is really taking 100 gig client signals, encapsulating those with G709 into a new optical transport network signal called OTU4. That OTU4 signal essentially includes something called forward error correction, or FEC. And what that does is allow for error correction and detection to make sure you can have error-free links over 1,800 kilometers. This does increase the bit rate for that single wavelength up to about the 112 gigabit range due to that extra added overhead. But that FEC actually provides a coding gain that can be measured in dB that helps to reduce the required optical signal-to-noise ratio. And finally, a modulation scheme that's known as dual polarization quadrature phase shift keying is used to squeeze that entire 112 gig signal into this little 50 gigahertz window of optical spectrum. And so since I mentioned DPQPSK, we might as well talk a little bit about what exactly that is. In the past, in order to increase the channel line rates, going from 1 to 10 was simply a matter of just increasing the symbol rate. Symbols were just binary intensity modulation. We could go from 1 to 10 with a single carrier without having to do anything particularly fancy. The commercial success of 10 gig has really led to quite a cost reduction of all these 10 gigabaud components. So instead of changing the symbol rate drastically, 100 gig has really looked into other ways of leveraging the existing technology and trying to find other ways to increase the channel bit rate. So dual polarization was one way to achieve this. You can take polarization multiplexers and basically double the channel bit rate by just simply combining 2 orthogonal polarizations. So this actually doesn't change the amount of optical spectrum that's needed, that's actually used on the fiber, but it still allows you to double the channel bit rate. So the graphic here that's highlighted in the red box is intended to help kind of visualize this concept. It shows how there's a horizontal and a vertical polarization that are multiplexed into one signal. And so in addition to keep costs low, you can even use a single laser and have 2 modulators to drive the cost down so you use the same transmitter for both polarizations. And so this technique turns out to work with or without something called coherent detection that I'll talk a little bit more about in a couple slides. But it turns out coherent detection is really the most cost-effective way to do this. So moving on to the modulation scheme, the other technique that's used to increase the channel bit rate and avoid increasing the symbol rate is to use this fancy modulation scheme. Instead of using something like on-off keying where we're turning the laser on and off, we're basically changing the phase of the signal of the optical carrier to encode the data. So in other words, phase shift keying. Quadrature phase shift keying just means that we're using 4 optical phases with each phase representing 2 bits. So this red box kind of sort of depicts in this constellation diagram where each of the red dots is a symbol representing 2 bits. So these two techniques have really reduced the required speed of the optical and electrical components drastically. We've cut it in half by a factor of 2 with dual polarization. We've cut it in half again by a factor of 2 with QPSK, to the point where it's now possible to leverage the existing CMOS available today and take advantage of all of that reduction in cost from that popularity of 10 gig that I was talking about. So here's an example of what this looks like from a spectrum perspective. In the middle, there's a 100 gig signal. This is basically 2 carriers spaced 20 gigahertz apart, with each carrier running at about 14 gigabaud. So what we basically have here are 2 carriers, we have 2 polarizations, and we have 2 bits per symbol from those constellation diagrams we just looked at. So what we end up with is these 2 14 gigabaud carriers turning into 112 gigabit per second signal. And I'll just pop up the channel spacing here, and you can see this fits quite nicely into a 50 gigahertz spectrum. The other thing that's clear here is that the spectral efficiency of these 100 gig signals is quite a bit better. There's actually less wasted spectrum. You can kind of see when you compare to the 10 and the 40 gig signal, you're using more of what's available there in that 50 gigahertz band, right? So I briefly mentioned coherent detection a few slides back, and I'm going to elaborate a little bit more on that. This is really the breakthrough technology that at least in my opinion, is changing everything. This was originally designed back in the 70s or 80s, but really optical amps proved to be a cheaper and easier way to improve the noise tolerance. So a lot of this work on coherent was largely abandoned. We started placing amps every 50 to 100 kilometers, and problems were basically solved, and we didn't have to worry about this. So the coherent detection has been sort of rejuvenated due to all the advances in digital signal processing. The number of gates, operating frequencies have all changed. So now we can actually process these kinds of signals and apply these sophisticated transformations in order to do this signal recovery, to do things like 100 gig. And really, there are 2 things that this is really changing. It's really leading to the elimination of needing dispersion compensating fiber. Chromatic dispersion is just simply no longer a limiting factor like it has been for 10 gig. And the other neat thing about coherent detection is that it really works like a radio receiver. You basically tune a local oscillator to the frequency you're interested in, so it's frequency selective. This has proved to be quite a breakthrough in optical filtering, because so far optical filter technology has been very disappointing. It's never really been matured to the point where it's cost effective, so things like colorless ROADM architectures have never really gotten very far, because the optical filtering technology has just never matured to the point where it's cost effective to do this. And finally, colorless ROADM, architectures are now being created now that this technology is here and becoming reality. So we'll finally really have the complete software reprogrammability of the optical layer using coherent detection. So once you bring this thing up, you're not going to have to move fibers around in order to, if you tune to a different wavelength, you're just going to automatically be able to shoot that wavelength wherever it needs to go. There's a few interesting side effects of this. One of them is that we no longer really need fixed optical filters. Components such as the arrayed waveguide gratings that are very common in DWDM systems would basically be pulled out and replaced with different kinds of components that are essentially just splitters and combiners and things like that. And if we no longer have a need for fixed optical filters, we don't really need a fixed wavelength grid. And so we really don't need to actually stay aligned to the ITU grid any longer. And ultimately, this is going to allow us to make more efficient use of the spectrum. We'll be able to pack in channels that require more bandwidth or less bandwidth. We'll be able to pack them closer and give them the amount of bandwidth they need. This is actually going to require new wavelength selectable switches that actually support this concept. But I think in time we're going to see this. So one interesting thing that has come out of all of this is that amp placement has become a really important issue. It's not just if you want to go above 100 gig to 400 gig or 1 terabit, but even just staying at 100 gig, we're starting to see the effects of amp placement issues driving the need for additional regens in the network. It can be a bit of a balancing act to some extent, right? You know, do I add another 100 gig regen here, or can I take some of my really long fiber runs and can I maybe break those up into some shorter spans and put an amp down in the middle of them and improve my OSNR. So OSNR is really what is, you know, the key factor in dealing with 100 gig and in the higher bitrate channels. The ideal amp spacing, you know, what your system is designed for is not necessarily going to match reality when you actually get into the field and, you know, get your fiber and you start looking at how long it is, right? So this has had some very real impacts on the advertised reach, for example, of our 100 gig long haul components, and has, you know, essentially driven us to need more regens than, you know, you initially think you're going to need. So just getting back to the flexible grid idea just for one moment. If you want to go up beyond 100 gig, at some point we're going to hit a limit where we're going to require a better and better signal to noise ratio, which at some point it's just not going to be achievable. And so, you know, one way is to go about, we could put ultra low loss fiber all in the ground everywhere, which is probably not a very viable option. You know, we're probably going to be stuck with the fiber we have for quite a while. So this is one of the reasons why flexible grid could be very beneficial, because we can simply throw more spectrum at the problem and not have to worry as much about the OSNR. So you can see what's being depicted here is, you know, your 100 gig channels and are using maybe, you know, a certain amount of spectrum, but, you know, once you get to terabit waves, you might give those 150 gigahertz of spectrum, and, you know, this would require, again, all the wavelength selectable switch components to support all this, but this is something that you know, it looks like it's likely to happen. Okay, my clicker is not working. There we go. Okay, so that's kind of the rundown on the 100 gig over the WAN, and just moving into a bit about 100 gig Ethernet transmission. This is I threw this diagram in here because I like the way it depicted how the packetization and you know, works with 100 gig Ethernet, because it's quite a bit different. They've really had to exploit parallelism throughout the design, and you see here, you know, the physical coding sublayer is really doing some sonnet-like functions where, you know, it's providing the ability to give you know, to avoid reordering and skew of the wavelengths. So it's adding very synchronous kinds of concepts to Ethernet to allow basically allow you to use 10 gigabit components and turn things into smaller and smaller signals and reorder them all when they come in on the receiver. And then here's a little bit closer look at what the inside of, for example, a 100 gig CFP looks like, right? And you have this thing, you have the physical medium attachment, and then the important thing here is this thing called the gearbox, the 10-to-4 gearbox. This is one of the things that you were going to see in the 10 by 10 CFPs, or sometimes referred to as LR10. It eliminates the need to have this gearbox. It can be quite a costly component. And finally, you know, this is just showing you how the 4 wavelengths, when they go onto the fiber, you have this possibility of some skew in the wavelengths, and these are all kinds of things that the receiver now needs to deal with. Is, you know, these wavelengths are going to come in, there's going to be skew and things associated with them, and that's what all those sonnet-like features that you saw on the last slide are you know, basically to give you the ability to deal with these physical effects of what happens after these signals go down the fiber. So on to pluggables, you know, at one point in our deployment, we were faced with the decision of do we go with LR4s or what's called 10 by 10. 10 by 10 are gaining popularity and vendor support. You know, we were unsure if this was actually going to work out for us, but what we eventually decided to go with the 10 by 10 here that I have highlighted in the middle, I'm sure you can probably guess one of the major factors for there was the $2 signs compared to the $3 signs. And so this was a very significant amount of money when you start multiplying things by 52 or so, or even 104, since you need optics on the transponders and on the routers, right? So this ended up being a non-trivial cost for us, and we ended up deciding to go with these 10 by 10 optics. Even though they were not an IEEE standard, they had significant industry support, and we were able to work with our vendors to make sure that these were going to work. So one of the things that I'll elaborate on this a bit more later, but it's the same thing with 10 gig and 1 gig pluggables, or any pluggables in your gear that you already have. Will it work or not? I mean, some vendors are going to lock it down, and you're not going to be able to use it at all, and they're going to force you to buy their certified optics. And some vendors will, it'll work, but it might not be very happy, and so it's the same kinds of issues we've seen with 1 gig and 10 gig, right? So in terms of optical power, these things are really hot. They launch at like, plus 13 aggregate. So, one of the things we found interesting is, we sometimes didn't even have power meters that could read that high, right? I mean, you plug the thing in, it just says high, right? It just says no, the power meter only goes to plus 10, for example. And I guess some of the things that we realized after starting to look at these were that you really can't test for compliance unless you have an optical spectrum analyzer. If you really want to see the per lane optical power across all 10 wavelengths that this thing is putting on the fiber, you really can't see what how much difference there is between the wavelengths, for example, or if you have one CFP that's a little bit better than the other, right? Because you might have out of a pile of CFPs, some might launch hotter on average, and you might actually get a little bit better performance out of ones that are actually launching a little hotter, for example. And just a few other things that we've just sort of random notes here. We've generally found that with the 10 by 10s, we could just plug them in. They engineer them nicely to be able to not need any attenuators when you plug them in back to back, for example. SR10 we really haven't had a whole lot of experience with, so we're still looking at maybe using this in some locations for hooking up hosts eventually, or something like that. But we've really standardized on 10 by 10, or also known as LR10. And that's sort of really the only pluggables we've really done any thorough testing of. We've done some LR4s in some limited cases, but it's really mostly 10 by 10. CXPs look very interesting. They claim to be, they're going to be interoperable with CFPs in terms of, you can plug a fiber into a CXP over here, and you can plug a fiber in the other end of it into a CFP, and everything should work fine. We have, really have no experience with CXPs yet, but. So anyway, we're turning up our first 100 gig circuit in October of last year, right? And this is a month before the big conference where we have to have all the 100 gig stuff working, and things are great. We can ping across this our first 100 gig channel, right? That's going almost across the whole country, which is very cool. We have about 40 days or so, and we actually do want to actually allow users to test this stuff before we actually have the show. And it was great to be able to ping, but we really wanted to show that under load this thing still performed well. Everything looked perfectly fine for the transport system. FEC was not like kicking in at all. It was just showing everything looking very clean. But we wanted to just drive it at 100% utilization just to really make sure everything was okay, and really measure zero drops, do some validation of QoS and things like that. And so the question became, well, how are we gonna test this? Because we don't have any 100 gig test sets. So how are we gonna generate this much traffic, right? And do we need to buy a 100 gig test box? So we have all these 10 gigabit perf testers already deployed everywhere. They're just basically hosts that have 10 gig NICs in them. And so we decided, well, let's have some fun with some routing loops. So we can take a perf sonar box, is what the boxes are called, that have these 10 gig NICs to our existing routers on ESNet 4. We hooked up a couple 10 gigs between ESNet 4 and ANI, which will be ESNet 5 soon. And we started basically creating some, basically just throwing in some static routes and starting making routing loops. And we carefully chose some TTL so that traffic would loop exactly the right number of times, and voila, we just just turn on an iPerf cannon, and instantly we have traffic looping 50 times around the network, and we can actually see the utilization go all the way up to 100%. So this was this gave us some good feedback that okay, this is we're not getting any errors on the routers, the transport system still looks good. We were pretty happy with this. So that was a quick way to just saturate the link and just do some sanity checks, and we're really wondering, can we do something a little bit more sophisticated and actually start counting packets and making sure we're really not losing any. So we started actually setting up policy-based routes for policy-based routing to do more complex loops. We're still doing basically sending just UDP traffic, but we're going onto the routers and essentially sticking in these policy-based routing configs and firewall ACLs to start counting back packets and measure loss and everything. And this just whoops, sorry. This just worked out great because I mean we fired this off and we were looping stuff around the entire network all across all those 700 gig channels that we brought up, and just zero loss. So that was really what we were looking for, and we're very happy to see that. And then we go and hand it off to the people who actually want to use it. So that was that. The next step was really to see, well, how does TCP perform on this thing, right? Because these are totally different gear that we've not used to. What we essentially ended up configuring here, it's unless you're familiar with this, it might be a little hard to see. NERSC is on the West Coast near Oakland, California. Argonne is near Chicago. In the middle there are basically our 100 gig links between Chicago and California. And what we had at each site as part of that experimental testbed on ANI that I told you about, we had a couple of hosts that are actually capable of each sourcing and syncing 40 gig of traffic each. So we have the ability to actually generate 120 gig of traffic and sync 120 gig at either end. So we started basically configuring some VPLS instances here and basically firing this stuff up. And here you can basically see that out of 10 streams, we were able to get basically 9.9 gig on each stream. The last couple were actually a little lower, 9.4. Those hosts are actually, it was just slightly different hardware rev that couldn't quite do as well. And at the very bottom there on the router, you could actually see the percentage utilization on the 100 gig interface was actually 99%. So this gave us good confidence that the TCP was going to perform as well as also, which we had a lot of concerns about. We did still find some issues with this, but I'll get into that in a bit. So at this point, we had sort of learned a little bit about, well, there were some certain things that were good about using host-based testers, and then we actually had access to some hardware testers as well. And that actually proved to be very valuable because they are very good at precisely controlling the packet content. They're very stable. Well, I don't know if I should say that actually. They're not always stable, but you can test a lot of different things, including things like reordering, which can be quite difficult to actually test with host-based testers. So I'm not going to read everything on this table, but we just sort of started writing down some of the advantages and disadvantages of hardware testers and the host-based testers. They both were very useful, and they both had their advantages and disadvantages. So we found with the host-based testers, it was very nice to actually be able to fire up real applications and start doing disk-to-disk transfers and see how stuff is really going to work when people hook up real hosts to this thing. So moving on, this, I make this all sound like everything was just great and we'd never had any problems, but, obviously we did. And, we found ourselves basically tracking down loss problems, tracking down reordering and things like that, and trying to figure out what was going on. We were not just, acting alone. We actually had customers who had routers that are other vendors, right, and connecting to us and connecting to other networks as they're using different gear, right. So we're sort of connecting a whole bunch of 100 gig stuff together that's all basically brand new. Lots of different vendors. Obviously we had some issues here and there, and we found that tracking down loss is pretty easy as long as you have accurate counters, and it's nice to be able to actually filter on like an IP address or something and be able to track down loss that way by counting packets. But when you have background traffic and stuff that, or you can't count with ACLs, it can be quite difficult to see if am I getting lost here, or where is this loss coming from. It's very important, obviously, to know where all of the drop counters are on your boxes. I mean, is it getting dropped, in some queue somewhere, or where is this loss happening that I'm seeing? So we spent quite a good bit of time tweaking QoS and all this to really figure out how to get this all running loss free. Tracking down reordering was quite difficult, especially if you don't have a hardware tester. We found some ways to do this using hosts, but we really liked using the hardware testers for this. We were doing things like capturing packet traces and all kinds of stuff, and analyzing these things and trying to figure this out. So it turned out to be quite time consuming to do so. Loopbacks tended, I'm sure many people have obviously learned the values of using loopbacks or debugging things like sonnet circuits, and we found that it was very helpful to be able to verify patching and things like that by going onto our transport gear, setting a facility loop facing the router, making sure we had the link come up on a port. We could quickly sanity check patching between the optical transport layer and the routers that way. So that was very helpful. You could ping, we could basically send pings to a broadcast address and make sure that we're not getting lost there. And it was just very helpful to be able to place loops in different places, either at the near end of the circuit or at the far end, to isolate problems. There were certainly a number of things that we had to work out, but eventually we got this all working quite well. So just a few notes on interoperability before we get to the end here. Between the transport gear and the layer 2 and the optical transport gear, we really didn't see any issues. I mean, the optical transport gear was just, bits went in, bits came out. It was just, as transparent as you could ever hope it, should be, right? It was, there was basically no problems, never had any issues. Between, layer 2 gear and layer 2, 3 gear and some other layer 2, 3 gear, we had various different kinds of issues. Remember, it's, 100 gig still quite new. We're dealing with products that are just out the door. Vendors have chosen slightly different ways of dealing with 100 gig and supporting 100 gig in their platform. So, it's really important to understand exactly how the flows go through your equipment. I mean, what is the interface on the backside of your 100 gig line card? How does it interface to the backplane? How does that backplane interface to the switch fabric? Can they actually handle a single 100 gig flow? Are they, doing something different? And understanding what schemes they use to basically internally load balance or something like that it can all be very important in understanding how to get good performance. So, we basically found that, not all the vendors were necessarily optimizing for one single line rate flow. And so this definitely led to some challenges that took some time to work out. So with our 10 by 10 CFPs, we certainly had some concerns with interoperability. We certainly went into this as a bit of an unknown as to whether or not this thing was going to like the 10 by 10, and is it going to talk okay with this other thing. After lots of testing through supercomputing, and after we basically ended up demonstrating basic interoperability, and by that I basically just mean these things could pass packets. They weren't always really happy that you stuck this piece of this pluggable in there, but things did, packets did flow, and they're not going to claim that your vendor is going to officially support this. They probably won't, but overall, we found that in general we could just plug these things in and they worked quite well. The support for optical power monitoring, in the CLIs varied quite a bit. I mean, some had it, some didn't. Some had per lane power, some had only aggregate power, some had nothing at all. So that was that was a bit a little disappointing, but not really a big surprise. Unfortunately, over short distances, we had no problems plugging in the 2-kilometer versions of the 10 by 10 into 10-kilometer versions of the 10 by 10. So that was also good to find out. And so just a bit of this is sort of some details about what we did with those 100 gigs that we took up to supercomputing. So near the beginning, I mentioned we had 100 gig from Salt Lake going up to Seattle. And so one of the challenges here was that another network, Canary in Canada, actually wanted to bring a 100 gig channel in as well. So we basically, had to work very closely with the SciNet wide area network group to figure out, well, how are we going to do this? And so what we ended up here with is that, the actual OEO conversion really happened right on the show floor at the trade show and down in Salt Lake City for our circuit. In the middle here, we had a couple of regens, so there were actually 2 regens required between Salt Lake and Seattle. And this is where it gets kind of interesting. So actually, once we got to Seattle, instead of actually terminating the circuit there in the Weston building at the POP, we actually handed it off to the domain that's managed by the SciNet WAN team here, basically as alien waves. So instead of handing them a 100 gig E client signal, we basically said, okay, here's an OTU4, right? Just keep transporting this over to the over to the show floor. And so these boxes that were between the Weston building and the trade show at the convention center were really just taking in alien waves, just doing the power balancing and pushing them across, and they actually didn't get converted back into 100 gig E until they got all the way to the show floor. So just a little quick case study there. Similarly, something happened basically with the Canary wave. It came in from Victoria, the University of Victoria, and came in again as an alien wave into the Weston building in Seattle and went over as an alien wave. So that's more or less it. In the future, we still have a lot of work to do, obviously, to finish the build, to do the transition. Some of the things that we're interested in looking at are actually, we're going to be mixing 10 gig on-off keying with the 100 gig DPQPSK. These technologies do not really play well together. We don't really completely understand what the impact of doing that is going to be. There is a reference here if you want to read more about it, but there are certain things that we're a little bit concerned about, and I think we're going to restrict ourselves to doing 10 gig in the metro areas to probably avoid a lot of these problems. But this is something we're interested in looking at. Deploying colorless ROADMs is certainly, hopefully, on the roadmap. Long-term flexible grid, if this concept ends up being commercially viable. Eventually, we want to do terabit waves and things like that. And so, just finally, before I end this, I just want to just acknowledge everyone who helped make this work possible. There's a lot of some people here in this room really helped make all this possible, and it certainly wouldn't have been possible to do all this without the rest of the ESNet staff and everyone you see here. There's some references if you're bored at night, you need to go to sleep. Any questions or comments? Oh, come on.
Don't everybody rush.
Hi, Will Hargrave from Lonap. I was interested in your comment about the 10 by 10 SR use in the data center, and I wonder whether if you think maybe we'd like to see greater failures of 100 gig links as a result of them just simply using more fibers. Because a lot of the failures of links I see in data centers is kind of like someone lent on the cable, or the connector was dirty or something like that. I wondered if you wonder whether that might increase.
Right. I mean, with the SR10, basically they have. My understanding is they have like MPO connectors, and you're basically going over multiple strands. So if you're doing something other than like rack to rack or within the same rack, you certainly probably don't want to go through patch panels and actually break out all the fibers and try to have this octopus cable going through patch panels and taking it somewhere else, right? So yeah, I don't really know how that's gonna pan out. I mean, I would probably feel comfortable, plugging a MPO into having MPO on both sides and being able to plug that right into a server or something like that, or a router. I think that would I could probably live with that, you know, from an operational perspective, but I certainly wouldn't want to start, you know, breaking out all those individual fibers and start, you know, I would just do single mode before we did any of that. So
That's the feeling I get as well. Yeah, thanks.
yeah. Thanks, Andrew. You promised me a question, so. Yeah.
Well, actually, it's Andrew Lee, Indiana University. It's just a quick comment. Pendleton was actually not an OEM. It might have been
Thank you.
NTGFF, but there weren't any transponders.
I'll have to blame Bill Johnston for that, so. Anyone else? We still have a minute and a half left. Well, thank you all very much. If anyone has any comments privately, feel free. Thank you.
Great, thanks, Chris. Next up, we have